Hello, everyone. My name is Michael Fu. I'm an engineer at Google. Welcome again to this session. I'm sure you've enjoyed interesting talks by the winners and authors. The original talk at this time slot was canceled, unfortunately, so I'm taking it over. As the last session of the day, I will keep it high level and provide insights about the competition from the perspective of hosts. I'll start by giving an overview, describing the participation, especially how the leaderboards were evolving over time, and what techniques pushed the breakthroughs. And then briefly go over the generation of the SDC data behind the scenes. And finally, I will end the talk about the legacy. First of all, for those of you who don't have a full picture of the general information, I'm listing out some key points in the following two slides to bring everyone on the same page. Similar to the competition in 2021, this year it was held for almost 3 months in the middle of the year. All data is published in this website, Kaggle.com. All general public is allowed to participate. They can download the data, submit the estimation results, and get an evaluation score for free. By the way, it is still accessible after the competition, which I will show some instructions in a subsequent slide. This is a joint effort co-sponsored by Google and Institute of Navigation. So thank you very much, Lisa, Miriam, and all other ION folks. In terms of the data, there are dual frequency L1, L5, and carrier phase measurements. So we use the phones from Pixels 456, Samsung S series, Xiaomi Mi A. Those are the phones that are most complying with the raw Android GNSS measurement APIs. And they are representing the best GNSS measurement quality. And we have 206 different drive tests. And this year, we are not only limited to San Francisco Bay Area, but also extended our test area to Los Angeles. And we also increased a ton of number of routes, different routes, to increase the variety and avoid overfitting to the environment. So in total, we have 86 hours in length, and all of the data are labeled with ground truth positions and velocities that are collected with Novotel span ISA 100C receivers with precise level arm compensation. And there are also info inertial measurement unit readings. At the end, the top 3 winner teams will share the 10,000 cash prizes and have sponsored attendance to this conference. So most of us paid to come here, but the winners of this competition came here and get paid. Well, the winners really went through a challenging process, which is partially illustrated in this slide. The total 206 drive tests or traces are divided into 3 sets: training, public test, and private test dataset. A score is defined over each of these 3 sets. It is the mean of the 50th and 95th percentiles of horizontal errors of one chase, and then average of all chases in each set. The training datasets takes around 80% of the total numbers, and their ground truth is publicly accessible by all competitors. And there may be up to 4 phones on each drive. And then the public test datasets has 28 chases whose ground truth is not accessible to the participants, but participants can still submit their estimations and get a score as an indicator about their performance. The score is displayed on the public leaderboard where everyone can see. One point that's different from the last year is we limit only 1 phone in each drive to prevent merging solutions that take multiple phones observations into one solver, which is less a realistic use case. And then the private test datasets has only the rest 8 chases. And not only their ground truth is not accessible, but also the score. After submissions, the score was recorded in the private leaderboard, but was not publicly available to all the competitors. But the private leaderboard will be published after the end of the competition, and the top 3 the top leaders are the winning candidates. One point I really want to emphasize is that those winners are not lonely soldiers in this battle. Instead, their success is backed by hundreds of competitors and lots of collegial discussions during the competition. I will show in these following slides about what I mean. So there are 571 teams, 676 competitors, and 9,940 submissions. The first place winner is Mr. Taro Suzuki, who was also the first place of the SDC 2021. He's from University of Waseda, Japan, very active GPS community member, and he uses a two-step factor graph optimization, or FGO. The second place winner is Mr. Subin Dai. He's a data scientist from China. He is a Kaggle competitions grandmaster, and he has won 38 gold medals. He uses a gradient descent for global optimization. And the third place winner is Mr. Tim Everett. He is an owner of RTK-lib Explorer, which is a very popular open source program. He uses a customized post-processed kinematic method without integer fixing. So two of the three winners are GPS experts, while the other one is a data scientist. This composition is representative of all the participants. If you see their discussions and code shared in this forum, you'll be impressed how efficient and effective those two groups of people are teaching each other. Their discussions are incredibly collegial and wide-ranging. On the left, I took a screenshot of popular notebooks. People are sharing all sorts of algorithms and utilities, GPS and machine learning included, with their own insights and lessons learned. Click into any one of them, you see the source codes and explanations. And then you can reference to it or build upon it. This happens regularly before the competition ends. The participants are really solving the problem together. On the right, I picked two discussions out from the forum. In the first one, the user Andrew was asking for detailed instructions of how to use RTK-lib. And the maintainer of RTK-lib Explorer, Tim Everett, showed up and answered him in detail. Shortly after this post was published, the public leaderboard was went up drastically. The second discussion is also a typical discussion. The user asked questions for the top winners. Are your solutions real-time? And then soon after that, another user came and answered. Many people, themselves included, I'm not using a real-time solution. They're using Kalman, something called Kalman smoothing. That means running the Kalman filter and then backward over the results, and then combine the two ways results appropriately. As you can see, asking questions and share knowledge is a very common thing, and it's a highly efficient way to solve the problems together. The outcome of this collegial effort in the community is reflected on the charts of the leaderboards. The left-hand side and the right-hand side show the changes of the top three leaders in the public and private leaderboards over time. X-axis is the time, Y-axis is a score in meters. Blue is the first place, red and yellow are for second and third place, respectively. And here are some of my insights. First, the breakthrough from 5 meters to 2 meters happens within the first quarter of the duration. And the second, the breakthrough from 2 meters to 1.2 meters takes the whole rest of the time, which is almost 3/4 of the time. And the second point is the breakthroughs were made by the leaders. For example, the RTK-lib, when Tim Everett introduced RTK-lib to the forum, and when Taro introduced his two-step FGO models. And then others followed very closely. And the third point is small improvements were made collectively through discussions and solution sharings. So one summary I can take is with common goal, common platform, common data, common metrics, and some award incentives. All of them enable successful and rapid technical advancements. We can get more insights if we overlay the trend of best score with the leading solutions. This figure combines the two leaderboards by taking a weighted sum. For example, like 80% of the best public school and 20% of the best private school. Because the participants like to share the solutions and source code publicly, we got to know what algorithms they are using. As you can see, the best score started from a weighted square solver. In the first 1 to 2 weeks, participants were getting hands on the competition and tweaking around the weighted square by ensemble or outlier removal. In the end of the second week, Team Everett joined the competition with his RTK-lib program and started to take over the first place for almost half of the duration. The team uses a PPK solution without solving integer ambiguities, which brings down the accuracy from 4.5 meters to 1.7 meters. Team likes to share, and he even made a Python wrapper for the RTK-lib C++ program, which made his program a very popular reference repository in the competition. The second stage, from 1.7 meters to 1.6 meters, started from about the middle of the competition. Akia Saito used FGO and TensorFlow, which is a machine learning library, to achieve similar performance as the PPK flow solution. Akio and team took turns to lead the public leaderboards in that month. At this point, their median horizontal error positions has reached the sub-meter level, so technically they solved the Decimeter challenge. But the score there was kind of lingering, and the community was waiting for a breakthrough. The third stage happened in the last 3 weeks. Taro Suzuki used his two-step FGO models to bring the best score down from 1.6 meters to 1.3 meters, or 20% improvement. As you can see from his talk, he has deep insights into GPS problems, and he has incredible hands-on ability. So I would like to congratulate Taro again, and thanks for putting an amazing ending to the competition. Again, I've put the relevant materials of these leading solutions in the links on the right. I'm sure you will benefit from reading them. Now I'd like to switch the gears to talk about the data itself and the work behind the scenes. In 2016, Google defined raw GNSS measurement APIs. Many people, myself included, believe that the phones can give you exactly whatever the APIs have defined and the values you requested for. But that's not the reality. For example, the phone may give you an invalid carrier phase measurement without properly indicating it. And it may miss half of the signals in the sky. Because there are a few chipset manufacturers, hundreds of phone models, and countless operating system versions, it is inevitable to miss the expectations here and there. Welcome to the smartphone GPS world. Indeed, the signal quality is one of the biggest challenges in the competition. To minimize the unnecessary hurdles, internally, we use this pipeline to prepare clean data and the ground truth. First of all, we have a dedicated vehicle with 3D printed phone mounts installed on the dashboard. And we have we use the mechanical arm to measure the lever arms from the ground truth receiver to the phone mounts, plus the phone's dimension numbers. Inside the phone, we use the two different logging applications to cross-check the quality of data logging. One of them is GNSS Logger, which is available on Play Store, and the latest version is just updated this week. When the collected data and ground truths are uploaded to the cloud, we use a set of filters to select and discard chases with obviously bad qualities. Next stage, we use an internal high-precision positioning engine to process the data. Compare with ground truth. And from the positioning metrics, the median, horizontal, cross-check, and align-check errors are our focus, because a large magnitude of them usually indicate systematic bias, such as incorrect level arms. The chases that are flagged out by the positioning engine will then be processed by the weighted square solver. Since the weighted square solver is a single epoch solver without many heuristics filters, it is very useful to review measurement or ground truth errors. The expected position error distribution should be a zero mean, Gaussian-like peak. The left figure shows exactly what we are expected. The x-axis is the east-west direction in meters. Y-axis is the north-south direction in meters. And the middle figure is an unexpected error distribution, where the errors scattered along the north-south direction, and it clearly needs further investigation. The right figure is another abnormal error distribution, and this usually comes from a wrong lever arm compensation. Chases with these abnormal patterns will be discarded. Before I jump to next slide, I would like to thank Taro Suzuki and other participants for discussion on this topic over emails and on the forum. This quality check pipeline selected 206 training and test datasets from almost 300 chases. And among them, the 36 with the highest quality ground truths were selected as the test datasets. However, after competition launched, we found 19 chases from the training datasets that have ground truth issues. We then posted a note publicly. We double-checked the test datasets, and fortunately, they don't appear with suspicious ground truth issues. Ground truth issue is not healthy to the competitions, and that's a challenge to us when preparing. But is there a ground truth for ground truth? Google spent a tremendous amount of effort to verify the correctness of ground truth. We are using Novotel's band ISA 100C. We verify its correctness to centimeter level using laser ranger. See these figures. The prism was installed on top of the car where the ground truth antenna is. On the ground, the laser ranger was placed still to measure the varying ranges of the moving vehicle. And that's the ground truth of the ground truth receiver. However, the ground truth receiver is correct in that setup and that scenario, but it is not reliably correct everywhere. That's what we found out, unfortunately. Therefore, we spend lots of human efforts to manually inspect the quality of the ground truth, hoping to deliver the best quality datasets to the public. Finally, I would like to use 2 more slides to talk about the legacy of the competition and advocate you or to continue using this data, platform, and metrics. So the artificial intelligence and machine learning community has a good habit to use open datasets for the standardized tests of their models. For example, in the figure on the top right, where large amount of images are published for training models to classify clothes versus shoes. Our GNSS community has not yet adopted similar standards. Currently, a typical smartphone GNSS paper will have very few real datasets to show results, and they usually have inconsistent metrics. Some likes to use median, some other likes to use rooming square. It's very difficult to compare which algorithms performs better. And this is the legacy of the competition. The Kaggle and the collection of more than 100 labeled datasets with verified ground truth can bring the GNSS to the research and development standards of AI. This slide outlines the detailed steps to download SDC data from Kegel and test your positioning algorithms, even after the competition. So they are there forever, and just a few clicks away. I won't go through the details here due to the time limit, but you can find them out in this slide from the ION website and also from the GPS World magazine website. With that, I want to thank you all for coming to this session and give thanks to ION for co-sponsoring. Thanks Brian, Dave, Luke, Tolu, and other Google and Kaggle colleagues for organizing their competitions. Last but not least, I want to give special thanks to all the competition participants. It's you who made the competitions great and benefited the whole GNSS community. Thank you.